Okay, in this video, we will discuss the Stark effect part. So it's a small problem. It's not a small problem. The conceptually what we have to discuss is a little bit small, but there is a lot of calculation. So I am leaving that part to you. You have to submit along with the other three problems. This is going to be the fourth problem. The calculation part, whatever is there. So we have to discuss Stark effect today. So before going into that, I skipped a small portion, a small topic that I wanted to discuss in the last video itself. So it's a theorem for finding out the ion functions of a degenerate perturbation theory. So the theorem says if we have an operator, let's say a cap is an operator, and that a cap is commuting with our unperturbed Hamiltonian. It's commuting with unperturbed Hamiltonian, and it's commuting with the perturbed part of the Hamiltonian. Okay, so if we can identify any such kind of an operator which commute with H prime and H naught in the degenerate subspace that we are taking, and also we have ion values, distinct ion values for A naught A cap, that is a ion values are not degenerate for this particular thing, they are different. So different ion values for A naught, and that corresponds to a set of states. Okay, so if you know any such kind of an operator with states with ion values which are different, they are not same, then that says you that if you take that particular ion vector phi and alpha, it will naturally give you this matrix that you want to diagonalize, and beta. These are the components that you want to diagonalize in, make it 0. But if this is a condition, you just take the ion vector corresponding to that A matrix, and this number is going to be 0. So the diagonalization done for you if you have taken the basis the ion vector as the ion vector of A cap. Make sure that if you take the ion values, for example, one is, if you are taking a two-state system, we can take operator A acting on, let's say, psi n1. It produces an ion value, and I'm taking it as mu, and psi n1. Okay, a cap acting on psi n2, that produces some other gamma. So psi n2 is mu, should not be equal to gamma. That ion value should not be degenerate. The problem with our H prime is that they are degenerate. So instead of that, if we have identified an A operator, and on that basis this quantity is also going to be 0. That is our diagonalization condition, and of course our job of diagonalizing is done already. So the cases where you know this quantity, it's quite easy to work on that kind of a situation. Okay, so that is something that I wanted to discuss in the last class. Now let us move to Stark effect. Stark effect. So Stark effect is actually, so you are putting a hydrogen atom just okay, I'll take an axis here. This is my electric field in this direction. And I'm keeping a hydrogen atom here with positive and the negative charge is there, which is the electron. So this is separated by a distance, and I'm taking that distance as r. Okay, if this is a uniform electric field along z direction, only having z component, so yeah, I'll take this magnitude of electric field. I will take epsilon, and this is along z direction. Okay, so first thing I need to know to do this kind of a problem using our perturbation analysis. So see, what we know is our hydrogen problem we know. Now the hydrogen problem is getting modified because of this electric field. So the electric field is acting as a perturbation here. So it some way modify. I don't know how it is modified. I have to find out what sort of modification is there for the hydrogen atom. So naturally we will use our perturbation analysis to find the energy correction, if any correction is there. So we have to find out that. Okay, so yeah, this is actually an equal charges, positive proton and electron separated by a distance, and it's nothing but a dipole. So a dipole kept it in an electric field, and you know the potential energy associated with that, and the potential energy equation is nothing but okay, what should I call H prime? H prime is nothing but your minus P dot E, your electric field. So P is the dipole momentum of that, and the dipole momentum, okay, let us take the origin as the nucleus itself. So the dipole momentum is going to be charged into that particular vector, that's going to be 0, and the separation into the charge, that is minus E into radial vector. So that is minus R E, and this minus and that minus will get cancelled, so that is plus RE dot E is epsilon z cap. Okay, I'll take this as a normal position vector. I can okay, with xyz coordinates, so I can get rid of this z dot product. So R I take xi plus yj plus zk, sort of. So dot product will give you nothing but R E epsilon in, and z value will be there. So as z h prime, this is our h prime, as it is an operator here. These three things are numbers, and this will act as an operator zk in the operator form. So this is going to be your perturbation component h prime. Once you identify that, we have to start putting the corrections and finding out the correction terms. Okay, first let me try to find out the correction, first order correction in energy in the ground state. Okay, we will do the ground state first. Ground state means n equal to 1. Okay, how do we represent the state here? I can represent state by using NLM. Okay, here we are not considering the spin of electron, that you have to specify. If you are considering the spin of electron, in that cases we will be discussing in atomic and molecular physics later. I don't know, we are discussing it in QM. No, I don't think so. So yeah, in that case we will be having an S coming along with the state. So right now we are considering the cases where spin is not considered. NLM is the state. So for n equal to 1, what and all states are possible for n equal to 1? N equal to 1, L can be 0, right? And of course m is also 0. This is only possible state for n corresponds to 1. Okay, now if you want to find out the first order correction, okay, this is not a degenerate state, so this is what we have to apply is our non-degenerate perturbation theory. So yeah, first how do you find out en1, first order energy correction? So this can be calculated by putting 1 0 0, that is a state, h prime inside 1 0 0. So this is the value whatever you are getting is going to be the first order energy correction, and yeah, you substitute that value, so you will get some value, and you have to put that value here. This is the first task for you. Okay, the question number 4, find out this quantity, first order energy, not only first order. So the question is find en1, that is first order energy correction, second order energy correction, and first order correction psi n1, and you can write the final wave function psi n. Same way you can write the en correspond after second order energy correction. So these all things you find out for this particular case. Okay, so yeah, that is for ground state. So from the perspective of degenerate perturbation theory, we have to discuss n equal to 2 case. So when n equal to 2 case, what are the possible values? NLM can take the values, or can take first when n equal to 2, L equal to 1, then m can take 3 different values, right? M can take plus 1, 1, 2, 1, 0, it can take 0, and it can take 2, 1, minus 1, and another possible state is L can take 2, 0, 0, 0 also. So these are the 4 different states which is possible at n equal to 2. Okay, now the question here is whether this is a degenerate system. All of these things are degenerate. What do you say? Is it degenerate? How do we understand? We know of course that the energy equation for hydrogen in particular, if you are writing En equal to minus 13.6 divided by n square electron volt, right? Hydrogen like atom, z square also will be there. For the case of hydrogen, it's nothing but 13.6 by n square. So it just depends upon the energy of a state, depends upon the principal quantum number n. For a particular value of n, obviously all the 4 states are going to be degenerate. So this was a degenerate system before the application of electric field, of course. Now once you put it in perturbation, what sort of change this is going to have. This is something that we have to find out. So how do we find it out? Well, the step 1 is to identify the degeneracy. Okay, so this is actually a fourfold degenerate system, and we don't know how many states are going to be lifted after this at this moment, even though we have seen it before. So okay, for this degenerate setup, we have to find out the first order energy correction. So first order energy correction, to find it out, I need to formulate a matrix, and that matrix element is going to be like this. First let me okay, matrix elements are going to be of this general form: NLM H prime NLM. So this is to make it different. All are having n equal to 1 and n equal to 2, that is same. So difference here is for L and M. So yeah, we'll find out this value for different combinations and fill the matrix. So our perturbation matrix HP is going to be okay, the first component. Okay, you can select any of them in any order. So you first label which one is which one, and sort of, so that the purpose is the whole thing will be easy. So I'll just take this one as my state 1. Okay, I'll just represent it with 1, and this is 2, this is 3, and this is 4 different states. So the first state is going to be 200. You can use the label. Once you label like that, you can use the label and find out the same components in that order. Okay, so yeah, first component for me is 1. I labeled 1. H prime, that I know, we already find out that perturbation, and 1, that is going to be the first component. The second component is going to be 1 H prime 2, 1 H prime 3, and 1 H prime 4. Okay, same way 2 H prime 1, 2 H prime 2, 2 H prime 3, 2 H prime 4. Same way you can fill the entire matrix. And next part is to find out elements corresponding to these quantities. So this is going to be okay, the exercise for you. Find out all these elements. 1 state 1 corresponds to, we have already found out what this state 1, or what is this 200 corresponds to, what is that state in the functional form. So you can put that in the functional form in the equation and find out the value. There are some parity considerations and all you can take if you want, if you don't want to solve it in other form. So some of the terms you can make it 0 using parity considerations and so otherwise you can just do it and find out the elements. And once you have done that, you will, okay, I'm skipping that part, you'll get the matrix like this. You'll get the matrix HP as -3 E epsilon a naught into the matrix components will become 0 0 1 0 0 0 1 0 0 0 0 0 0 0 0 0 0. This is going to be the matrix HP matrix.